Okay, so the question was, is it really true? Does adding one clean qubit, and of course many of you know the answer to this, many of you know about one clean qubit computing, but the answer is yes, it does, and I'll just talk around it a little bit, so to give you my impression about why it works. Here is, again, this complexity space. I have purged all the bullseye out of it and just included a bunch of states in here. The simple states are at the center. The maximally complex states are outside, near the boundary. And that's the setup. This is this complexity geometry. And the overwhelming majority of states are out in this somewhat darker region here. Now, my view of computation, as I said, is that there are a certain family of states which we could call target states. Target states are the states, if you can get to them, you learn something interesting about the question you are asking. For example, supposing there was a question, a numerical question, what's the value of such and such? And the value happens to lie between -1 and 1. Supposing we can arrange to find places where the expectation value of the first qubit, let's pick one qubit, where the first qubit, the expectation value of it, is equal to the solution of our problem. If we can navigate to one of those places and then make a measurement, we have to do it several times, depending on how much accuracy. We may have to do it 100 times, 1,000 times. But by navigating to one of these places and then making measurements and collecting statistics, we learn something about the solution. Okay? I haven't told you how to navigate, but imagine that we did know how to navigate. So I say the goal of computation is to guide the system to a target region. Incidentally, I've drawn the targets more or less at a sort of common complexity. All right, so here's the cartoon. A computation starts with a very simple state and navigates to a target point. Notice that the computation always moves outward, which means it's sort of satisfying the second law of complexity and doesn't require going down in complexity. What happens if we were to start the computer out at maximal complexity out here? Then all it does is wander around for endless amounts of time, doubly exponential amounts of time, in this doubly exponential number of enormous states out here. It takes an incredible fine-tuning to aim it back toward the center. And so that's why your computer sort of becomes useless once it reaches maximal complexity. But now let's add that one clean qubit. When you add the one clean qubit, what happens is the geometry gets bigger. In fact, the maximal complexity doubles. I'll just describe that by saying the geometry gets bigger. That's number one. And number two, at least sometimes, more possible target states appear out at larger complexity. If this is the case, you have a chance then of starting in this very complex, previously very complex situation and actually getting to a target, if there are targets out there. And there's good reason in some cases to believe there are targets out there. If we come back to it during the prolonged discussion period, which will happen after the talk, you can ask me why I know that there's a, okay. All right, here's an example. The example is one clean qubit computing. There's some unitary operator which I write G because it's a product of gates. It could be a product of gates, doesn't have to be. Imagine whatever G is, let's suppose we can represent it as a product of gates. The minimal number of gates would be the complexity of it, of G, and we're interested in calculating the trace. Why is the trace classically hard to compute? There's n qubits here. The dimensionality of the space is 2 to the n. To calculate the trace, you have to add up 2 to the n numbers. Not much, I don't think there's much shortcut. And so it's a very complicated and complex problem to calculate the trace of a matrix. You have a box. There's a matrix in the box. I'm not going to tell you what it is, but what we can do is we can stick it into a circuit. And we can run a circuit, and the circuit will spit out the value of the trace. Okay. So here's the circuit. This is familiar to people who know about one clean qubit. You have a maximally complex state. It's usually stated in terms of a maximally mixed density matrix, but it doesn't matter. A maximally complex state, a single extra qubit. You hit the extra qubit with a Hadamard, and then you do a bunch of controlled operations where you apply the gates if the spin is down. You don't apply them if the spin is up. You apply a Hadamard at the end, and then you measure the Z component of the extra qubit here. Okay? What is true is the expectation value of the Z component is equal to the trace that you're after. All right? So you do this a few times, I don't know how many times, 1,000 times or whatever, and you get a good estimate of the trace of the unitary matrix. At the same time, because these gates will generically tend to increase the complexity of the circuit, they will also decrease the uncomplexity of the circuit. And the amount of uncomplexity that you lose will be roughly the complexity of the unitary whose trace you calculated. Okay. We have done computational work. We have spent a resource. What does uncomplexity have to do with gravity? I'll try to go fast. Everybody knows what this is. This is a Penrose diagram for an eternal black hole in ADS with 2 copies of the ADS CFT on both sides here, blah, 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 blah. This is Alice's black, these are 2 entangled black holes. This is a thermal field double state. This is Alice's black hole. This is Bob's black hole. And because they're entangled, they create a wormhole in between. And this is the wormhole region. This is Alice's side. This is Bob's side. One thing which is true is, despite the look of it, this is time homogeneous. This is time homogeneous, and both sides are in perfect thermal equilibrium. Nothing happens in here. Nothing happens in here. But something is growing in here. The question is, what is growing in there? From the CFT point of view, from the quantum mechanics point of view, what is it that's growing? In some sense, it's the volume of the Einstein-Rosen bridge that's connecting them. But the thinking is, my thinking, and by now maybe 2 or 3 other people's thinking, is that it's the quantum complexity of the state, of the CFT state, which is growing. That it's actually the quantum complexity of the state which is growing, that represents the growth of the wormhole. On the other side, you can ask what's growing from the geometric point of view. So I'll tell you now about the connection between complexity and action. Take the time, t, and think about the quantum state of the boundary theory at time t. You might think that's dual to some kind of notion of a state in the bulk which lies on a space-like surface connecting the left side with the right side. But that's not the right way to think about it. The right way to think about it is it's the state on all possible space-like surfaces which are anchored at the 2 ends. And the union of all those space-like surfaces is called the Wheeler-DeWitt patch. And it forms a sort of diamond, which is cut off at the singularity here, but it forms a diamond. This region would be called the Wheeler-DeWitt patch. And this region would be the portion of the Wheeler-DeWitt patch behind the horizon. The hypothesis is that the complexity of the state is essentially the action. You can take it to be the space-time volume of the portion of the Wheeler-DeWitt patch behind the horizon. As time goes on and the Wheeler-DeWitt patch time moves up, I'll do it again so you can see it. The volume in here grows. It grows outward from the ends, and the way to think about that is some kind of computation which is taking place on the horizon of the black hole is being holographically encoded in the interior step by step by step as the black hole evolves complexity. Here's another example. This is the so-called one-sided black hole. This is not an entangled black hole. It's just a pure state black hole. Has only one side. Again, it has a Wheeler-DeWitt patch. And again, the state complexity of this is thought to be equal to the action or the space-time volume of this region here. Okay. Again, you run it, time goes up, and the space-time volume increases. That we take to be the increase of complexity. Let's go back. Let's go back now. Alice, at time t, has a state vector describing let's say, the boundary field theory. And according, if she knows all of this, she'll say that the complexity of the state is equal to the volume of this region. That's kind of interesting. It says that the complexity is the volume of everything that Alice cannot experience. Why can't she experience this region? It's just too late. She can't jump into here. She can jump into here. All right, so the complexity from a geometric point of view is just the entire volume that Alice cannot experience, according to this connection between complexity and whatever. On the other hand, the maximal complexity, the maximal possible complexity, is the volume of the whole thing. Now, I've put a cutoff here. That cutoff is supposed to represent what happens when the complexity gets exponentially big. It gets cut off. Can't grow bigger than exponentially big, so I put a cutoff there to represent that. And then the maximal complexity would be the volume of this. So let me go back. This is the complexity. This is the maximal complexity. The difference between them is the uncomplexity. And that's this region here. What is that? That is the region that Alice can experience. The entire region that Alice can experience, the volume of it, is a kind of resource. It's the resource of space-time that Alice has available. That's what she gets to look at. That's what plays the role of the uncomplexity geometrically. Let's suppose that the black hole is exponentially old. All right, let's suppose the black hole is all used up. It's gotten to be exponentially complex. It would follow from this line of reasoning that there should be no accessible space-time behind the horizon. No uncomplexity, no accessible. That fits rather well with the firewall argument, one of the firewall arguments. One of the firewall arguments said that a generic black hole, and I believe this argument, a generic state of a black hole has a firewall at the horizon. The only difference between what I would say and what the AMPS people would say is that generic means maximally complex, not maximally entropic. The AMPS people thought that a black hole reaches its sort of final generic state at thermal equilibrium. That's a very short time, a scrambling time. In fact, quantum states reach their generic behavior at an exponentially large time. All right, but still, I think the statement is correct, or may be correct, that at an exponentially long time, a firewall will develop. Okay, so let me go a little more. Here's a picture of a black hole with a firewall. Alice cannot get in. If she tries to get in, she'll hit the firewall. This is connected with Stanford and Schenker's shock waves. And in fact, you should probably think of a firewall as a sort of shock wave very close to the horizon. Now Alice says, wait a minute, I want to get in. What do I do? Well, she has a qubit. The qubit means a thermal photon, a thermal wavelength photon, very long wavelength photon. Long wavelength photon carries one bit of information into the black hole. She has one thermal photon, which you can think of as one clean qubit. What happens when that thermal photon hits the shock wave? Well, you might think nothing, because the shock wave is enormously energetic. But now this is a pure gravity, no complexity theory, pure gravity. The one clean photon hits the shock wave and gives it a push. This is calculable. I call it the Drey-Tuft effect. It pushes it in and exposes an entirely new region of clean spacetime. And that clean spacetime lasts for another exponential time. The black hole, the interior of the black hole, is rejuvenated for an exponential time, in precise parallel with the one clean qubit effect.